Okay, so oh, sorry, so we have worked our way to question 3. So I'm just doing the questions on my half, of course. So we've worked our way to question 3, so we'll continue from there. And as we go along, please do ask me any queries, or if there's anything that you'd like clarified, please do stop me and ask. So the next part, so in question 5 was, it's got half of it from Saeed's half, complex numbers, and root finding of complex numbers there. And then the second question is on one of these modular arithmetic groups. So this says, write down the Cayley table for the group, say 15 multiplication, so you need to understand what that means, and identify all its cyclic subgroups. And I think back in 2014 I did a little bit more on this, but the final part is explain briefly how the statement of Lagrange's theorem is verified by this example. So Lagrange's theorem is contained just at the very end of chapter 5 on page 72 after the exercises. It's quite easy to understand. It says that for any finite group, the size of any subgroup is restricted. The size of any subgroup has to be a divisor or a factor of the size of the containing group. So it's quite an interesting result that restricts the possibilities for subgroups. And we'll see that being exhibited by Z15. So to answer this question, first of all, you're going to have to explain clearly what this group is. So Z15 is the group of integers under multiplication modulo 15. Okay, so it's not a normal multiplication, but multiplication modulo 15. Now we explained when we looked at these that when you're considering integers modulo 15, you only need to consider the integers 0 through 14, because every other integer is going to be equivalent or congruent to one of those. Okay, so the integers 0 through 14 form a complete, sometimes called a complete residue system, modulo 15. But for considering these things under multiplication, and in order to have a group, just come around this way, please, because there's a wire. In order to form a group under multiplication modulo 15, we can't have all of the congruence classes modulo 15. We have to only consider those that are coprime to 15. Okay? Because having a multiplicative inverse modulo 15, you need to be coprime to 15. So as a set, Z15, the superscript multiplication sign, contains only those congruence classes of integers coprime to 15. So we can say Z15 is going to consist of those n between 0 and 14, such that the greatest common divisor of n with 15 is equal to 1. Okay, that's what being coprime to another number means. So as a set, we can identify those elements. 0 is not coprime to 15 because 0 is divisible by 15. So the greatest common divisor of 0 and 15 is 15. 1 is certainly coprime. 2 is certainly coprime. What we're doing here, of course, is the prime factors of 15 are 3 and 5. So we're not going to include anything which has a factor of 3 in it or a factor of 5. So the 3 is excluded because the greatest common divisor of 3 and 15 is 3. The 5 is excluded. The 6 is excluded. Just come around this way, please. The 6 is excluded because it has a greatest common divisor with it has a greatest common divisor with 15 to 3 also. So the 6 is excluded. The 7 is included. The 8 is included. The 9 is excluded. 10 is excluded. 11 is included. 12 is excluded because it has a factor of 3. 13 is included. And finally, 14 itself.
Did I get those all right? Did I miss out any or include any wrongly? I don't think so.
Good. The ones I've excluded are 3, 5, 6, 9, 10, 12. So these are the elements, okay? So this is going to form a closed, complete system under the operation of multiplication modulo 15. The identity element is clearly 1. Okay? So you multiply anything by 1, it remains the same. And you've got all these other elements here, and we'll discover when we lay out the table that each of these has an inverse under multiplication modulo 15. So the Cayley table is the name given to the multiplication table for this group. So to form one of these, you lay out all the elements as headings for the rows and columns of the table. You don't necessarily have to list them in the same order, but it's strange not to. And in the body of the table, we're going to put the product of the two entries under multiplication modulo 15. And normally, when you're doing Cayley tables for a group, you have to follow the convention that the entry that goes in here is the row index on the left multiplied by the column index on the right, similar to the way that the double indexing of matrix entries works. The first entry, the entry on the left, is the row index. The second entry, the entry on the right, the double index is the column index. For this group, we don't need to be so cautious because this group is a commutative group. The operation is commutative, okay? Because multiplication modulo 15, okay, that's based on regular multiplication of integers, which we know is, or which we accept is commutative. So strictly speaking, we only have to worry about filling in one of the triangular halves of this table. The other half will just be a reflection of its opposite half. Okay. So going across the top row, 1 by 1 is 1. That's easy enough. 1 by everything. 1 is the identity, so 1 won't change anything. Now for the other entries, you're just working out the product in the normal integer multiplication sense and then reducing it modulo 15. 2 by 2 is clearly 4. 2 by 4 is 8, 2 by 7 is 14, 2 by 8 is 16, so it's the first one we have to start reducing. 16 modulo 15 is 1. 2 by 11 is 22, which goes to 7. 2 by 13 is 26. 26, which goes to 11. Sorry. And 2 by 14 is going to be 13. You can speed up slightly on your completion here because it's a property of groups that every row and column of the Cayley table is going to contain each of the group elements once and only once. So along any row or down any column, you're going to see the complete set of group elements. So that can help you fill in the last remaining. Of course, this one here, I'll write in green, the ones I'm just putting down by reflection. So keep going. 4 by 4 is 16, which is common to 1. These ones here I should already know. 4 by 1 is 4, and 8. 4 by 17 is 28, which is 13. 4 by 8 is 32, which is 2. 4 by 11 is 44, which is 14. 4 by 13 is 52, which is 7. And the only one remaining is 11, so it has to be 11. 4 by 14 is, what is it, 56. And 56 is 11 greater than 45, which is multiple of 15. Okay, so we go for the next row. So this is going to begin 7, 14, 13. Because that's how that column behaves. And this row is the reflection of that column. And so, we don't have far to go. We just got this lower triangular bit to go. So 7 by 7 is 49, which is 4 greater than 45, so it's 4. 7 by 8 is 56, which is 11 bigger than 45. 11. 7 by 11 is 77. Divide that by 15, 45, 60. So that's 2, isn't it? 7 by 13, well, 13 is minus 2, so it's going to be minus 14. That'll be 1, I think. And 7 by 14, 14 is minus 1, so it's minus 7, so it's 8. Some of the when the numbers get very big, you can start to think of them not as their values that they are there. You can start to think of them as the negatives of smaller numbers. That can help you work out the products as well. So 13 I thought of as minus 2, so 7 by minus 2 is minus 14. 14 is the same as minus 1, so minus 14 is going to be minus 1. So we can keep going here then for 8. We've already got 4 of the entries, and we 8, 1, 2, 11.
Why did you put 7 by 4, 13, 3?
Because 7, 4, 13 agree. I'm putting the green ones as just the reflection of this half up here.
Okay.
Because the group operation is commutative. So A by B is always equal to B by A for this operation under multiplication modulo 15. So A by B is something in the top half. B by A is its reflection in the diagonal in the lower left half. And 8 by 8 is 64, which is 4. 60 is a multiple of 15. And yeah, and actually, once you've gone halfway in each row, you can actually complete it as it'll be all the negatives of the ones coming away from the center. 4 is the negative of 11, so 2, so it's going to be 13, 14, 7. Okay, how did I know to write down 13, 14, and 7 there? Well, you see, wondering about what was 8 times 11. This is going to be this 13 here. What's 8 times 11? Well, 11 I know is minus 4. So 8 by minus 4 is going to be the negative of 8 by 4. I've already got 8 by 4 here, which is 2. And the negative of 2 modulo 15 is 13. So you can, once you started filling out this table, you can shortcut a lot of the subsequent entries. And okay, so come down to 11. I've got most of this already. 11, 7, 14, 2, 13. And we've gone past halfway here, so 13 and 2, so 14 and 1, 7 and 8, 11 and 4. And this isn't true in general for KD tables of groups. It's not true in general that each row is kind of a mirror reflection down the middle, but it is true for these modular multiplication, and it's a consequence of having the entries laid out like this, where the second half of the entries are all the negatives of the entries coming in the first half under reflection down the middle. So
So 13, we've practically got it all there. 13, 11, 7, 1, 14, 8. And there's just 2 remaining. It's going to be 4 and 2. And lastly, 14. Well, we've already got the whole of that. Or you can think of each entry here is just going to be the one remaining one that isn't present in that column already. 14, 15, 11, 8, 7, 4, 2. What have I got there? I've got 1. 14 is -1, so -1 squared. -1 by -1 is, of course, 1. So that's our Cayley table there. So most of the marks, I think, would have been going for completing that. It also asks us to identify all its cyclic subgroups. So remember, a cyclic subgroup is the name we give to a subgroup that is grown or generated out of a single element. So these are important in group theory. It's the simplest way, if you like, to generate a subgroup, just to take one element and see what you can manufacture out of just that one element by using the group multiplication. Okay. So a cyclic subgroup takes the form. Looks like this. This is the notation for g to the power n, where n is an element of the integers. And we understand this g to the power n to mean g multiplied by itself n times under the group multiplication. And if it's a negative integer, it means g inverse multiplied by itself n times. But in the case of a finite group, we can just consider this as since the group is finite, we can just look at the positive powers, because we know, because the group is finite, eventually if you just look at all the positive powers, eventually you're going to come back to the identity element. You have to come back, you have to repeat. So this cycle of elements is going to complete in the cycle and come back to the identity element. So in this range of positive powers of that element, you will find the inverse of G. Okay, so let's look at these. Well, the cyclic subgroup generated by 1 is automatic, because what can you get by starting with 1 and using multiplication? Well, 1 times 1 is 1. 1 times 1 is 1. You can't go anywhere really apart from where you already are with 1. Cyclic subgroup generated by 2. Okay, so in combination with using your table, so you're looking at 2 to the power 0. Remember, anything to the power 0 by definition is the identity. 2 to the power 1 is 2. 2 squared is 4. 2 by 4 is 8. 2 by 8. 2 by 8 is 1. So you're back to 1. Okay. There's no point in going through looking at any higher powers of 2, because 0, 1, 2, 3, 2 to the 4 is 1. There's no point in looking at 2 to the 5, because 2 to the 5 is 2 times 2 to the 4, and we've already got that here as 2. If you look at higher powers of 2, you're just going to continually cycle through those 4 elements. So that's a subgroup of order 4. Let's look at 3. What do we get when we work with 3? We get 1 and 3 anyway. Oh, sorry, 3 isn't included. 3 isn't included. 3 isn't present. 4, you just get 1 and 4. Okay. 4 to the 0 is 4. 4 to the 1 is 4. Sorry, 4 to the 0 is 1. 4 to the 1 is 4. 4 squared is 16, which is back to 1 already. 7 is the next element. So what you get with 7, you get 1 and 7 anyway. 7 squared is 4. 7 times 4 is 13. 7 times 13 is 1. Okay, so it's another different subgroup of order 4. Different to this one over here. 8, subgroup generated by 8. Subgroup generated by 8 is actually just the same as this one. You can kind of explain that by noticing that 8 is the inverse of 2. 8 is the inverse of 2. So an element and its inverse will always generate the same cyclic subgroup. 11. 11 is another one of these 2-element subgroups of order 2. So 11 squared is 1, you see from your table. 13 generates this one up here again, because 13 is the inverse of 7. And 14, well, because 14 is minus 1, that generates another order 2. So these are all the cyclic subgroups that can be found in this group. So there's 1, 2, 3, 4, 5, 6 distinct cyclic subgroups. We notice that Z15 itself is not cyclic. Okay, because none of these are the whole of the group Z15. So that's interesting to see. Some groups are cyclic, some aren't. And a bit about Lagrange's theorem. Is respected here as it must be, since the order of Z15, how big is Z15? It's size 8, isn't it? There's 8 elements in it. So the order of Z15 is 8, and we only see subgroups of sizes 1, 2, and 4, which are all factors of it.
Excuse me, what's the after N?
Lagrange. Lagrange. French guy. Since we only observe cyclic subgroups of sizes 1, 2, and 4, i.e. factors of 8. This is a bit hard to set. Any questions or queries about that? So you should be confident we're working with addition, modulo, any modulus, or multiplication, modulo, any modulus, and in completing these Cayley tables. And if you want to complete them efficiently and save time, you can, well, in the cases of these ones anyway, of all the modular arithmetic groups, they're all commutative, and make use of the fact that the lower left triangle is a reflection of the top one. That can speed you up. And then considering the negatives as well can speed you up as well. So there's a few bits and pieces left that come from my half the course. There's the whole question 6, and then half question 8 as well. So we can have a look at those. So question 6 is about differentiation, and the first part of it is a bookwork proof. And it's asking you to prove this basic property of the derivative, that it is a linear operation. So I would certainly kick this off by giving the definition of the derivative. That's key here. You're going to have to be using that, so you need to get that down. So the derivative, where F and G are mentioned in the question, so I'll talk about H. The derivative H prime of A of a function H, let's say from the real numbers to the real numbers, is defined as, so H prime A is defined as the limit as x approaches A of the relative change in value of the function. Change in value of the function, which is the numerator h of x minus h of A, relative to the change that we've introduced in the arguments, which is x minus A. And we're looking at how that relative change in value of the function behaves as x approaches A, closer and closer to A. And then it becomes this number, if this limit exists, if it's a nice enough function to have a derivative, this limit exists, this becomes this number, which embodies the instantaneous rate of change of the function at the point A. So now, so we let alpha and beta be any two real numbers without any restriction. And let f and g be two functions differentiable at A. So our task here is to show that the linear combination of the two functions is also differentiable. Okay, so it's a very nice property of the derivative, and it shows that the derivative meshes well, interacts well with these two important ways of forming new functions out of old, namely taking scalar multiples of functions, if you like, and adding functions. Linear, which that whole combination of those two we refer as linear combinations. So alpha f plus beta g, this new function, the derivative of this at A. So there's a question mark now over, does this limit exist? And if it does exist, what is it equal to? And it's those two matters that we're going to settle here. Well, the limiting process that it is this, so we simply repeat the definition, but this time we're working with the function alpha f plus beta g. So it's alpha f plus beta g evaluated at x minus alpha f plus beta g evaluated at A. That's the limit of that relative change in value. So the first step here to do is to expand that numerator according to the definition of what it means to add functions together and what it means to take scalar multiples of functions. So the limiting process you leave alone. For now, still over x minus A. And expanding this all out, we'll have alpha f of x plus beta g of x minus alpha f of A minus beta g of A. And the thing to do now is, now we've got the individual f's and g's free, so to speak, isolated and on their own, no longer bound up together in these brackets. So they're now free floating. So now we can bring all the f's together and bring all the g's together and separate out the fraction. So we'll do all that together in one step. This fraction is equal to this one. So the justification for that is just simply algebraic manipulation of this numerator and just splitting apart the two fractions. The rules for additional fractions. Justification for getting to this second line here. This was the definition of linear combination of functions. From here to here is just kind of algebraic manipulation of that thing. Just a word of caution in the class test, we did notice some incorrect manipulation of fractions, symbolic fractions. So if that was the case for you, if I did write comments to that effect on your class test, just take note of that and just make sure, revisit the rules for symbolic manipulation of fractions and just make sure your every manipulation you're doing is correct and that you're simplifying fractions in the correct way. Okay, now what we're going to do, you see now it becomes clear what's going on. This is exactly the relative change in f. This is exactly the relative change in g. And you're taking a linear combination of those two. Alpha times this plus beta times this. And then we're taking the limit of the whole thing. So we're taking a limit of a linear combination of things whose limits we know to exist because it's assumed at the top that f and g are both differentiable functions. So we've assumed that the limit of this exists and the limit of this exists. And it's a known property of the limiting process that we can reference, that we proved previously, namely that the limiting process respects linear combinations as well. So the limit of this linear combination of things is equal to the linear combination of the individual limits, and those individual limits exist. So this is alpha times the limit as x approaches a of f of x minus f of a over x minus a, plus beta times the limit as x approaches a of g of x minus g of a over x minus a. And the justification that we're using there is kind of crucial. So this is true by the algebra of limits theorem. And the assumption that f and g are differentiable. So the new limits exist. These new limits introduced here exist. And of course they are exactly alpha times the derivative of f at a plus beta times the derivative of g at a. And what we were dealing with all along here was the definition of the derivative of alpha f plus beta g. So alpha f plus beta g is now differentiable, we proved, and its derivative is equal to that nice expression. So therefore we can say alpha f plus beta g is indeed differentiable at a. So if f and g are differentiable anywhere, so will alpha f plus beta g. Is that okay? Any questions about that? we looked at 6 part B. 6 part B is more an application of concept of the derivative. So you're asked to find derive from the definition of the derivative what the derivative of the function hx equals x cubed is. Okay, so we're considering this function h, which is h of x is defined as x cubed. So the derivative of h at a point A, so at a point A in R, the derivative of h at A is by definition this limit of these relative changes, the relative change. H of x is x cubed, h of A is A cubed. Now this limit poses a problem when you look at it first, because you're taking a limit of a fraction, and the top part approaches 0 as x tends to A, as does the bottom part. So it can't be evaluated by simple substitution of the limiting value of x into this expression. Also, it wouldn't be reasonable to use the L'Hopital's rule here, which is applicable in this kind of case, to evaluate a limit of a fraction which is evaluating as 0 over 0. You could use L'Hopital's rule. However, in order to use L'Hopital's rule, you'd have to use the fact of what the derivative of x cubed is. But we're in the middle of an argument about trying to prove what the derivative of x cubed is. So it'd be unreasonable to use the fact that you're trying to prove it. So we have to deal with this without L'Hopital's rule in a more primitive way, so to speak. And we can deal with that is because, see, in this limiting process, x is never actually equal to A. So this denominator here is never actually equal to 0. And it is possible to divide it into the numerator cleanly and get a nice remainder, okay? Because this numerator does factor symbolically as a polynomial. And the way it factorizes is you can take out the factor x minus a, and that leave behind x squared plus ax plus a squared as the complementary factor. If you didn't remember that factorization off the top of your head, it is possible to rederive it if you remember that, okay, let's say, okay, I remember it's possible to take the factor x minus a out. Well, you're a bit hazy on what the complementary factor should be. Well, you can recreate it fairly easily. Whatever the complementary factor is, it has to multiply by x minus a to get x cubed minus a cubed. So it certainly has to have an x squared in it, if you like, because it needs an x squared in it to multiply by the x to get x cubed. However, once you put an x squared in it, you're then going to generate a minus ax squared. So you're going to want to get rid of that. And you can get rid of that by introducing a factor ax. Because if you have ax here, you'll get a plus ax squared when you multiply it by this x. Ax times x gives you plus ax squared. So the problem introduced by introducing this x squared can be eliminated by introducing that factor. But then introducing this factor introduces a slight problem because it introduces a minus a squared x, which you don't want to leave behind. So if you don't want to leave behind an a squared x, you can add in a plus a squared here, which will give you a plus a squared x over here, which will cancel with that minus a squared x introduced here. And this process could go on forever. Each time you introduce a fix, it introduces a new problem, which you have to fix again, and so forth. So on, except the problem here stops because the potential new problem introduced by introducing this bit, the a squared, it gives us a minus a cubed. But that's not a problem because that's exactly that's the rest of the expression that you need. So then you say, okay, yeah, I remember that's the formula. Okay. So you can regenerate these factorization results, and they follow a pattern. So like if you had x6 minus a6, you can also take out the factor x minus a out of that, and the complementary factor follows the same pattern. It's x5 plus x4a plus x3 a squared plus x squared a3 plus x a4 plus a5. It's the sum, what you get in the complementary factor is the sum of all of the order n terms, or so let's say the order n minus 1 terms, where n is the order of the thing you started off with. So this was order 6, thing you started off with. So here we have the sum of all the order 5 terms in the product x times a. See the total index here, the sum of the exponents is always 5. Okay, so once you have it like this, you can notice that when you take the limit as x approaching a of this, in that limiting process, x is never actually equal to a, so we're free to divide by it. Remember that there is a problem if you're trying to divide by 0, but we're not dividing by 0 since x is never equal to a. So those two can cancel now. So we're just left with the limit of x squared plus ax plus a squared. But now we're taking a limit of things, and each of the individual things, there's no problem with working out what its limit is as x approaches a. X squared is going to approach a squared. A times x is going to approach a times a. A squared is a constant, so it just keeps its value as x approaches a. So you've got a linear combination of 3 things here. Each of them is differentiable. Each of them has a limit. So therefore, the limit of the linear combination is just going to be the sum of those 3. So this is going to approach a squared plus a squared plus a squared. So in other words, 3a squared. And this holds at any point a. Okay, there's nothing special about a. The fact of some fixed point in the numbers. So therefore, this holds for all a. Derivative of h, this function is equal to 3x squared everywhere as a function. Okay, I'm going to have to leave it there for this morning, I'm afraid. But Saeed will see you now, and Saeed will see you tomorrow afternoon as well. And also, I will be putting up work solutions to the last 2 years of exams, last year's and the year before that. They'll go up pretty soon on Moodle, so do have a look out for those. If you've got any queries at all, if any queries come up, feel free to email me. I should be